So Marcus, I think we can start now with our session. First, thank you all for joining for this session. My name is Tim Bosidlo from INTAMSYS. I would like to give you a warm welcome with a session that we do together with Victrex. And Marcus, therefore, I have one question that I would like to clarify with you today. The question is it possible to get close to isotropic parts with materials like PAEK?
Sure, and certainly we'll try to attempt to answer that, Tim, during the course of the next half an hour.
Marcus?
Yep.
Yeah. So one thing to all attendees that is very important, please. If you have questions within the presentation, use the chat function, write your questions inside, and we will answer them in the end of the session.
So Tim, there, can you see the slides now? Anyway, this is so as Tim said, there'll be a few minutes at the end of the presentation where you can certainly ask some questions, and we'll do our best. My name is Marcus Jarman-Smith, and with Victrex, I help people solve complex design and engineering challenges using the polyketone family of high-performance polymers. And I've been doing this for around 14 years. And INTAMSYS is one of the pioneers of high-temperature polymer printing, and I'm delighted to have been given the opportunity to let you know about the latest state-of-the-art in high-performance polyketone polymers, which can work with systems like their FunMat HT and especially the latest Pro 410 and 610 HT printers. So today I'll show you how a new polyketone material called AM200 can give you an additional tool in your toolkit of options for solving problems and making parts for your customers. Now, you may already know about the family of polyaryl ether ketones, or PAEKs, high-performance polymers, and this is the group name covering such family members as PEEK and PEC. But what you might not know is that the very properties that make these materials so attractive to use as functional materials in thousands of applications also make them difficult to print. So in the next few minutes, I'll explain what the high-performance polyketones are, how they're used, and why they're a challenge. And then I'll explain why we at Victrex are working together with innovative and pioneering machine manufacturers like INTAMSYS to bring next-generation polyketone materials to the marketplace. And the main difference being that these are the new PAEKs, a new generation that are specifically engineered for the 3D printing world. So hopefully by the end of this webinar, you'll know that you can access through INTAMSYS not only the latest high temperature machines, but soon to come new polyketones like the AM200 that I'm going to show you. You'll get to see how this latest material, AM200, has improved interlayer adhesion, and as a consequence of that, better mechanical properties, especially in that all-important Z-axis. And you'll also see how AM200 can be printed at lower temperatures, lower than PEC or PEEK, which potentially makes it more accessible. And you'll also see the possibility to print amorphous then anneal, or on some printers even print directly crystalline, so reducing the need for secondary steps, saving time and money. So At the heart of Victrex are the PAKE polymer family, so collectively called this polyaryl ether ketones or polyketones, of which family members like PEAK or polyether ether ketone is probably the most well known and widely used since Victrex invented it some 40 years ago. And since then, Victrex have been working to enable engineers to get the best from these very specialized materials and use them in new ways to solve problems and create their own value. And the great thing about these materials are that they simultaneously possess many beneficial properties at very high levels of performance. And as such, they sit at the top of the polymer pyramid. And PAKE materials can be considered for many cases where you just wouldn't normally think a polymer could be used. So high temperatures, extreme chemical environments, and that sort of thing. And because of these great physical, mechanical, and chemical properties, polyketones are already used in thousands of high demanding applications across these kinds of industries. Check out the recordings of INTAMSYS's first and second sessions to find out more about the properties and how they can be used as metal alternatives as well. So, so you could be working on parts for aerospace, and due to the lightweighting, fire retardancy for ducts and brackets, deep in the sea for chemical and temperature resistance in like seals, or even in, under the skin where the right grades of polyketones can have the purity and biocompatibility and put shock absorption into the body as well. So this slide shows some of the many applications that our Victrex PEAK has been certified and used for. But many of these applications demand a certain level of properties. And these have been achieved through traditional processes such as injection molding. So therefore, whilst the properties achievable today through 3D printing can still open up a wealth of applications, it's only when the properties begin to reach those of their injection molded counterparts that we believe 3D printing truly opens up to more possibilities. So typically, the properties are things like chemical resistance and high strength, and a lot of this is due to the molecular arrangement of the materials. So on the left-hand side, you see if there was a polymer that was an amorphous structure, it's generally a disorganized arrangement that is typically described as a plate of spaghetti. And these materials tend to flow more readily, whereas materials like PEAK tend to be more of the structure, as you see on the right-hand side, this semi-crystalline structure. And interspersed within the amorphous areas are areas of organized areas, the lamellar and spherulite areas. And these give the polymer this structure and rigidity. So typically the properties for amorphous polymers can be good impact resistance, but they can be more prone to things like stress cracking or poorer fatigue resistance. Amorphous polymers, amorphous versions are often transparent, or they have that translucent honey color. So on the right hand side, the PEAK kind of polymers, where they're semi-crystalline, typically are anisotropic in flow, which is shown by the arrow diagram at the bottom. And this means that there's greater shrinkage transverse than with the flow, and the risk of potential dimensional instability, which is why warping and curling can be an issue as each layer is printed. And of course, the latest generation of printers like INTAMSYS Format Pro 410 or the 610 HT are pretty sophisticated and seek to provide the right conditions for the demands of these existing polymers, but they are challenging to print. And of course, the degree of crystallinity can affect the properties as well. So for example, PEAK with the structure, as I said, like on the right, is typically 30% crystalline. And this is what gives it its great properties, such as good strength and wear and chemical resistance. So different PAIC family members can have different crystallinities, or the same family member can even have different crystallinities depending on temperatures that you expose them to. So for example, PET can have amorphous or crystalline grades available. So some applications you get asked for may be more than covered by the end properties of an amorphous version, if the demands of temperature or chemical resistance are lower, for example. And typically amorphous versions print more readily. But as I said earlier, to get the maximum value from these polymers, ideally we'd like the end properties of the 3D printed versions of these materials to be in line with the types of properties that we can achieve through traditional processes like injection molding, which are usually semi-crystalline. So ideally we want an anisotropic print, but resulting in properties near to the values of a semi-crystalline injection molded part. So that's the gold standard, which is obviously no small ask. So here you can see outlined some of the challenges that I've mentioned here, and for both the current AM technologies that are capable of processing PEEK and PAICs, there's been some challenges which have limited the potential of additive manufactured parts. And as part of the whole ecosystem approach, we're finding ways to achieve and enable better 3D printing of polyketones through several factors, through re-engineering the materials, through working with pioneering high temperature machine companies like INTAMSYS, and even exploring completely new processes that may be more compatible with the existing traditional versions of the polymers. So in the end, the aim is being really to give the market options and enable different ways to get functional parts from high performance materials. So why did we think re-engineering the polymer would help? Well, as I mentioned with semi-crystalline PEEK, the current challenges for 3D printing can be seen here in this DSC trace, which shows how the standard PEEK polymer behaves. Along the top of the trace, you can see it melts at about 343 degrees Celsius, which is 649 Fahrenheit. So a high temperature for a polymer. And then along the bottom of the trace, it recrystallizes rapidly at around 297 Celsius. So this happens fast and doesn't really allow layers much time to bond. The PEEK materials are engineered for melt processes such as injection molding, where the whole material is melted at this 343, but residence times and cycle times in injection molding are typically quite short. So the polymer is not held for long at these temperatures above the melt, and it doesn't get time to degrade. And the whole kind of setup is typically within a closed system, not subjected to oxidation, which can also cause polymer degradation. So on the lower part of the trace, you can see the rapid peak of recrystallization at 297, and then this gives it peak its characteristic 30% semi-crystalline properties, the chemical resistance and high strength. So the additive manufacturing process obviously is very different, with longer residence times and in some processes hours or even days. And depending on the process, there can be localized areas of melt interacting with solid materials. The print builds up. And the build chamber is usually in an air environment where the bulk material can be held at temperatures just below melt for long periods of time. And these are all not optimal situations for the traditional polyketones and mean that the resultant parts are often less than optimal. And the physical and mechanical properties can suffer, such as become really brittle. And of course, the advanced INTAMSYS HT printers try to compensate for this with these traditional polyketones, and they've got many features, such as high chamber temperatures, bed and nozzle temperatures are high, and even things like heated filament storage chambers. So they're really working to try and optimize working with these traditional materials. Additionally, for printing using filament fusion, the high viscosity of the traditional PAIC materials can also be problematic for the machines. Here you can see a rheology graph for PEAK at 380, and it shows how the viscosity goes down for PEAK, making it flow more easily when the shear rate goes up. Now, normally in other melt processes, work is put into the polymer in a screw or a pressurized system where the shear rate becomes high and then the material begins to flow more easily. But obviously for 3D printing, the material stays in a state that is more like the left-hand side of the graph, which is in a low shear state and hence higher viscosity as it comes out of the nozzle. And this high viscosity can cause sticking and disruption in a consistent flow. So recently, Victrex have commercialized a new additive manufactured polyketone filament, and this is called AM200. And it's made from a PAIC polymer, which is specifically engineered for additive manufacturing. And AM200 is a high performance polymer, but it's able to be processed at much lower temperature, so 303 Celsius than standard PEAK, which is 343, or PEC, which is 335. And the DSC trace that you can see here for this material, AM200, compared to the PEAK one that I showed previously, the AM200 trace here is in green, and it melts with a broader temperature range occurring around that 300 point, which is obviously less of a hurdle for some machines to handle. And the lower part of the trace shows the recrystallization at 250 degrees Celsius. And you can see the green line of AM200 is broader and flatter, and it allows the molecular movement for longer and allows the fusion between layers. And this reduces the chances of poorer interlayer adhesion, and it tries to overcome requiring extra optimization steps in the deposition strategy, like contouring or infill patterns and skirting. So we're progressing towards more stable printing. When we take another look at the rheology graph of AM200 here in red compared to the PEAK from before, we see from the red line of AM200 that the initial viscosity is much lower than the blue line of the PEAK. PEC would sit somewhere in between these two. AM200 is less viscous at low shear rates, meaning that good flow is possible through the nozzle at the shear rates that we commonly experience in filament fusion. And this is generally reflected by their easier printing at these lower temperatures. So what you can see here is really to sort of visually tackle one of the main current concerns with filament fusion, especially with PEAK, and that's of course the interlayer adhesion and avoiding the delamination of parts. So the images here show test samples printed in the Z direction. When we do a 3-point bend test, and we're pulling the test samples in such a way that we're actively attempting to tear the layers apart, what you can see here is on the left for AM200 sample, you can see a jagged fracture surface. So this indicates that the sample didn't delaminate as easily at the layer interface, and it's much stronger. And as a consequence of that, we're seeing improvements in the performance of printed parts. On the right-hand side, you can see a shiny area, which is a flat fracture surface on the peak sample. And this is where it delaminated partially along the interface between the printed layers. So it's a consideration for your choice of material, depending on the job and the part that you're making, but it obviously depends upon the key end user requirements and the demand placed upon that end part. So here we see some properties of printed AM200. The left column shows benchmark data for tensile properties, and this is the data from injection molded PEEK. So we're using this as if you will, a gold standard, acceptable for all those applications I showed at the start of the presentation. The middle data shows typical properties for printed PEEK obtained on a range of machines from across the industry. You can see tensile strength in XY in the range here, 60 to 70 megapascals. For Z, 10 to 30 megapascals. And then in the last column on the right, you see some typical properties obtained for AM200 derived from machines, again, from across the industry. And here you can see an XY in the range 60 to even 90 megapascals, which is really like injection molded. And for Z direction of 40 to 70 megapascal. So with regard to properties obtainable from printing, again, it really depends on the machine and the profiles and how these are tuned. So the great thing about collaborating with INTAMSYS is the amount of time and effort that they put in assuring that the combination of AM200 and their HT machines work really well. And the aim here is to end up with a total solution. And on the left, this understanding began with development of profiles and optimizing these over time to push the properties achievable for the Z direction. And the bar chart that you can see on the right-hand side shows some data from printing AM200, firstly amorphous, which is the first two bars on the left of the graph, where there's a fairly good XY, but especially the Z properties are achievable up there at 62. And these may be enough for many applications. Amorphous can give precision parts and more ductile material, and as you can see, is still pretty strong. In the center of the bar chart, you can see two bars for semi-crystalline AM200. And the main thing here being that the XY values are pushed that much higher to quite an impressive 78 megapascals, whilst the Z is around the same value that we saw for amorphous. And then the two bars that you see on the right-hand side are a benchmark reference for PEC, which you can see is lower in the Z-axis there. So Victrex AM200 can be printed amorphous or crystalline, and it depends on the specifications of your printer and your process settings. On the left-hand side is an example of a manifold with amorphous AM200. And as I showed on the previous slide, the properties are still pretty impressive. And you can see the part here with this, this really nice honey color. On the right-hand side is a semi-crystalline version of the part, which improves properties such as the chemical resistance, the fatigue resistance, and the temperature resistance, especially above 150 degrees C. So it really depends where the part will be used. Now, Victrex AM200 provides this flexibility for you to choose which method works best for your application and depending on the equipment that you've got. So you can print amorphous and leave it amorphous. You can print amorphous and post anneal it, or you can print directly crystalline with certain printers. So for example, if you if you're lucky enough to have the INTAMSYS Pro 610 HT, you know, there's a 300-degree build chamber and bed in that machine. So in summary, then, Victrex AM200, it's a new PAIC. It's specifically engineered for 3D printing. Its lower melt temperature means that high-performance polymers become more accessible. Earlier, you saw the rheology and how it flows easier than PEEK or PEC, and how it makes it easier to print. You also saw the slower, lower crystallization, which can help interlayer bonding, which should make it less likely to stress and warp. And you also saw the flexibility for you to choose which method works best for your application and equipment. So again, you can print amorphous and leave it amorphous, you can print amorphous and anneal it, or directly print crystalline. So one grade that allows you that flexibility. And you also saw the interlayer adhesion and how that boosts the ZX strength and allows the properties to be near isotropic prints. So I hope you've seen that there are growing and increasing options becoming available to you, and to enable you to print quality parts from high performance polyketones. But of course, materials are only part of this equation. And so now I'll hand back to Tim, who can tell you a little bit more about the high temperature machines for printing these functional materials.
So Markus, thank you very much. I think the results that we got so far with AM200 are really impressive. And I think we're looking both to each side that we need each other. Yeah, so we can build the best machines, but without a good material, they're useless. And you can build the best material, but without a good machine, they are useless. Yeah, so thank you very much for this very good presentation about AM200. Now I would like to give you a short introduction our printer portfolio. So we have high temperature printers, starting with the FunMat HT, which is a really desktop-based high temperature printer with already a 90-degree heated build chamber. Then we have a Pro 410, which is a more industrial build machine with a dual extruder printhead, a water-cooled printhead, preheating filament chamber, and a lot of very good accessories. Yeah. And then on top we have the Pro 610 HT with a 300-degree chamber, which allow you to print parts with AM200 directly in the crystalline state, which allow you to avoid annealing and avoid a lot of time in post-processing. Yeah. Yeah. I think, Markus, can you skip over to the next slide? Thank you. So if we are going back to our question, is near isotropic filament fusion printing with high performance polymers such as PAEK possible? My personal answer after this presentation is definitely yes. No, it's or yes, it's near isotropic. I think for filament fusion technology, we are getting really impressive results. Already 65% of injection molding tensile strength in the Z axis, which is very, very impressive in my opinion. So thank you very much, Markus, for presenting AM200.
Pleasure.
So now I would like to spend a bit time, if you have questions to Markus regarding AM200 or to INTAMSYS, to our machines, please feel free to ask them now in the chat. You can send them privately or you can send them in the group chat, and then we will try to answer them for now. So we got one question that is related to mechanical properties in general from AM200, also with elongation, I think this is a very long question, so I would like to skip this for now and take this into a private conversation. So Merve Başak Kanal, please feel free to contact me or Marcus later on, that we get closer to you to give you more information about elongation, z-axis, and so on and so on. Yeah. So Marcus, we have here another question that I do see, and this is from Alex. Would it be possible to do the recrystallization of PAEK into the 610 during the printing process?
So I guess this goes back to my earlier comment just around it really depends on the printer and the setup that you've got. So there's a lot of factors that are involved, and you'll need to carefully control those conditions. So as we mentioned, with the latest sort of generation of the INTAMSYS printers, this is something that you've got more flexibility and can do, just because that machine is so much more sophisticated and powerful. So it is possible to do these things. It just really depends on the profiles that you've got set up and the equipment that you've got at your disposal. So
yeah, thank you. Very good answer. Marcus, I have another question for you from someone in a private message, so I will not name him. The question is AM200 biocompatible? Or is it planned to maybe get a biocompatible version of AM200, or is that not possible to the process or whatever?
I suppose very briefly, these materials, the classification are very well known for medical uses. The thing that makes these materials a medical and an implant grade of material is all of the testing that has to accompany that. So AM200 at the moment is still, as you see, a very brand new polyketone material. Obviously, it's got a lot of testing that's been done with it, but this isn't the medical testing. So it would need to go through quite a comprehensive remit of biocompatibility testing and studies in order to get that certification. So it doesn't have that currently. I guess the most famous material that is used is the Peak Optima grade of PEEK. That's used for implants and is proven biocompatibility. But if you want to achieve that with other grades, then you do have to do a huge amount of testing to prove that out. So we're not saying that that's not something that won't happen in the future. It's just that it does require an awful lot of testing and time with the studies. So it's not something that it has at the moment.
Yeah, I think certifications is a point for itself, and this is really related to a target group. So thank you for this very good answer. I see there two last questions that we got, and I will ask the first. Will be AM200 available in form of pellets, or will it be only available in filament form?
So it will be available in a filament form, so not as a pelleted material. And as I mentioned, this is a really state-of-the-art material, and so it will be available in the forthcoming weeks. But it will be firstly available as a filament, a 1.75 mil filament for the FDM machines.
Yeah, and I think with this you already answered maybe our last question, and the question is AM200 available for purchase? Yeah.
Literally, it's hot off the printing press or 3D printing press. This really is a state-of-the-art material, and one of the great things about Formnext is that you can come and see what is really is the latest developments, and so it's available commercially now. Will be available over the next few weeks, and we're pleased to say that we're collaborating with INTAMSYS as well. So yes, you will be able to obtain this material in the next few weeks.
Yeah, and I would like to add one thing to this, one point to the last question. INTAMSYS will be the first reseller worldwide who will distribute this material. So if you have any request for purchasing these materials, please feel free to contact us. Also, if you have more questions, notice our email address and come later back to us again to answer your questions in detail. I would like to say again, thank you very much for joining. Thank you, Marcus, for such a great session, and good luck for next.
Pleasure, and thank you to the audience for taking the time to join us online. It's appreciated, and have a great rest of the show.